Okay, welcome everyone to my continuation of what is linear algebra. Today I want to discuss or to explain what is a dual vector space. Okay, and this is, in my experience, usually a very tricky concept. Not because it's really hard, but maybe because it seems to be a little bit unnatural. It falls a little bit out of the blue. And if you're not used to this very basic concept of duality, kind of science and mathematics, then it looks really weird. So today I'm trying to explain it. It might not be completely weird. So it doesn't fall out of the blue. It's just a very natural thing to consider. In the end, the abstract formulation is a bit tricky to work with, but it's not so bad. So let's jump into it and, well, try to understand what's going on. One of the main reasons I think why the dual vector space is so complicated because you just basically start. It's your first. Usually, it's your first uh, um, encounter of something like duality in mathematics or whatever. So let me try to explain kind of the philosophy behind duality. And this is really a super general concept. So if you understand dual vector spaces, then you're on good track because there will be a lot of other dualities in mathematics and beyond that are modeled around the same thing. It's really like a coin, and you have two different sides, but they are kind of they're of course different, right? Heads or tails, but they're not so different at all. And whatever you can say about hats, you could say it about tails as well. It's completely well. It doesn't matter how you name it, right? It doesn't matter what the names are. You can just play one against the other. And this is kind of the whole idea behind duality. So here's my wish list. So let's say I would have to cook up duality in mathematics. And let's say there's something, and of course I call it V because in the end it will be vector space, but for now V is just anything you can think of. And there will be some dual thing. And I call it V star. And star is kind of the standard notation for duality usually, or it's a standard notation for duality. And my duality, what should it do? And this seems to be a little bit unmotivated, but you will actually see this very often in practice. And the dual vector space will be one example of these. So certainly, well, the first one is actually quite okay, I think. So the dual of the dual is the thing you start with. So doing it twice is like doing nothing, right? If you have a coin and you're looking at heads and you flip it, the dual is tails, and you flip it again, you're back with to heads. That's kind of a natural thing to assume. And the other ones are a bit trickier, but you really want those in practice as well. So there should be not just a duality on spaces, but there should be a duality on operations, on theorems, basically. So let's say you have something, a linear map, an operation from V to W, then you should have a dual operation. An operation from, well, what is a dual operation? It kind of turns everything around. So that's what you should remember about duality. It really turns everything around. So an operation from V to W will be an operation from W star. So that's kind of the point. Here's a star. So the W changes. So W goes in front. V goes to the back. So it changes around. An operation turns into an operation, flipping everything around. So an operation from V to W turns into an operation from W star to V star. It's really two sides of the same coin, and everything flips around. In particular, like the order of operation or the direction of operation. And then there's something well related. So any operation has a dual, has really a dual operation. So there's a one-to-one correspondence from operations in one direction to operations in the other direction. And kind of the main philosophy behind duality is it's hard to explain. It's not like you can write down a definition or whatever. So, like Atiyah said, duality in mathematics is not a theorem, but kind of a principle, something that works surprisingly often and is really, really powerful, and it's really worthwhile to understand it. So, basically, every statement that you can think of that is true about V has a dual statement. A dual statement that is true about V star. And then if that's a philosophy and this is works in practice, then you're in business. Why? Well, because maybe you want to say something about V, but might be a bit complicated. V star might be easier, and you just prove something about V star, and now you know it about V as well. That's pretty cool. So you can basically play both sides against one another, and whatever is better for you in the situation at hand, that's what you do. So it's really, really, if this works, right, this is really good because now you have basically two similar things, and one of them might be better, and you just pick the one that is better. Um, and you kind of all know an instance of this, and it's really everywhere in mathematics. And I can only talk about mathematics, but I kind of believe that it's kind of everywhere in life. They're always kind of, life tends to be binary. Okay, this is not true, of course, because life is not mathematics. It's not true in the strict sense, but in some sense, life tends to be binary, and kind of everything has kind of a flipped side. Um, in mathematics, life is much better because in mathematics, we just define everything to be binary anyway. Okay, I'm just waffling. A theorem that you all know that has a counterpart is something like 2 points meet in a line. So here, 2 points, 2 points meet in a line. 2 points meet in a line is perfect. Two lines meet in a point. So two meets in one. Or dually, for 2 points, you will always find a line that such that, well, 2 points meet in one line. That's what you could call this one here. And two lines meet in one point. It's kind of a dual statement. Right? Two meet in one. Okay. One meets in two. No, two meet in one and two meet in one. Just one of them is point and the other one is line. Okay, so what I really want to sell is this idea of having some kind of two sides of the same coin that are kind of inexchangeable. Think of either of them, whatever you prefer. It's good. But whether you prefer lines or points is kind of unimportant for the theorem to be true. Okay, but that's just a general philosophy. And if you believe in this philosophy and that it's kind of everywhere in mathematics, let's say that's a fact of life, then what you want to do is you want to see how this works for vector spaces. Because, well, right now we are looking at vector space, we're doing linear algebra. And all of you have seen some kind of duality at one point. I mean, you can write a vector as a row vector, or you can write so whatever, x, y, z, or you can write a vector as a column vector, right? You can write x, y, z. That seems to be a matter of taste. These are really kind of dual concepts, and I'm trying to explain this right now. So you have the standard inner product on, let's say, R3. Doesn't matter so much. It's just component-wise pairing and multiplication. And the fun is now I want to see every row vector as an element of R3. So my convention is row vectors are elements of R3. So what are then column vectors? So the other way around. So column vectors are elements of R3, the green one here. So what are row vectors? Row vectors, well, in matrix multiplication notation, like this one here, they take actually a column vector and return a number. So this is just a number here, because you just component-wise takes a sum. So they turn an element of R3, a column vector, into a number. And that's what's called a one form. Just a fancy name for this is a map. Actually, each row vector gives you a map from R3 to R just by pairing, just by writing down this number here. So what's the difference? Okay, one of them is actually a vector in R, and one of them is a vector in the dual space. And it seems like the dual space wants to be something that is a map from R3 to R. Okay, and there's of course a one-to-one correspondence because the only thing I did is, I basically decided not to draw column vectors anymore, but to draw row vectors, and that's it, and that's a choice. So each vector in R3 and R3, there's nothing special about R3 here, right? Each vector in R3 corresponds to a linear map given by pairing and vice versa. Each linear map given by pairing corresponds is basically one of those things in some reasonable way, and you get a vector out of it. So it seems like there's a duality between from row to column vectors. Maybe that's the right thing to think about because, again, in some sense, who has decided that row vectors are better than column vectors? They're exactly the same information, so why not? And indeed, that's kind of what you do. And let me try to do it again, this time for R2. So you can think of R2 as being all column vectors. And a column vector is something, let's think of it like a map from R to R2. What is this map? Well, it takes a number and it produces just the scalar multiple of the vector itself. So each vector is actually a map from R to R2 in some sense. Right? If you consider the number 1, it just spits out the vector. If you consider any other number, it spits out, here you go, the column vector 1, 1 spits out the line through 1, 1. Right? That's interpretation of this map here in terms of column vectors. In terms of column vectors, yes. So a column vector takes a number and gives a vector. And this is just saying it's a line. It's a column vector corresponds to a line, right? All scalar multiples of this column vector, that's a line. The dual space are row vectors. And I already write our square dual. And this is, again, this is the opposite. It takes a vector and gives a number, which is the corresponding pairing. That is, right, this one here, just for R2. And if you want to illustrate that, that's a little bit weird because it takes a vector and gives you a number. What you can do is you can illustrate this geodesics. So you can say for any fixed value here, so I fix a value, and for any fixed value, I get a line. Okay. Whatever. So all of those lines here fixed value is 0, you get a line. So for each one of them, you get a line. And this is a row vector 1, 1. And a funny fact, it's orthogonal to the column vector. It's just more it's the same information illustrated in a different way. So it's kind of a two-dimensional object. Anyway, so the point is one of them are row vectors, one of them are column vectors. Row vectors, column vectors, right? And that's the dual. That's exactly the dual. So the formal definition is now for the dual vector space, that's just all, well, let's see. So all endomorphisms here from R2 to your ground field R. Okay? All endomorphisms from R to R2, and formalized, this is what it is. All endomorphisms from V to K. And this is just saying, this is really just saying, in the finite dimensional case, it's just saying, yeah, let's take row vectors and not column vectors. These are row vectors. And what you can do is, well, you get exactly what you want. Let's say we're, so So duality is usually very tricky for infinite dimensional things. Let's ignore that. Let's say we're a finite dimensional case, then you get exactly what you want. So the dual of the dual is a dual, and this is actually canonical in some sense. And a matrix from V to W gives you a transpose matrix from W prime to V prime, from W star to V star, and similarly. So this really checks with our definitions from before. And you can do something like this. If you start with a basis, you get a dual basis given by basically the delta functions. So evaluation is 1 if the indices are the same, and 0 else. Okay. Anyway, that's just a formal definition, and it's very nice. But basically, what's going on is you swap the notion of row and column vectors, and for maps would be you swap the notion of a matrix and its transpose. So it's kind of the dual map. So the F star here, the dual map is the transpose matrix. So duality on vector space is pretty harmless. At least in the finite dimensional setup, it's basically transposing everything. And it kind of makes sense, right? I mean, who told you? So I'm always getting confused. If I write down a matrix, I'm always getting confused. What are the rows? What are the columns? And of course, this is just a choice someone made at one point. And the dual just says, well, okay, you could have also done the other choice. It really doesn't matter. And obviously, any theorem you can prove about a matrix A, you can prove it about the matrix transpose. Right? So basically, everything has kind of a dual statement. Everything you can prove about a column vector, you can prove it about kind of a row vector. Everything is a dual statement. And that's duality for vector spaces. It's actually pretty harmless. It just comes in usually in a slightly abstract formulation as all k-linear endomorphisms from V to a ground field. Basically, you want to formalize of transposing vectors and matrices. Okay, some pictures to end with. So in some sense, everything kind of turns dimensions around. And that's a general philosophy that I want to sell here anyway. So at the very beginning, we saw that kind of everything turns around in order. And you can see it explicitly in those examples. We really some kind of dimensions turn around. So a column vector is basically just a one-dimensional thing, right? It's a line. And a row vector is kind of a the hyperplane. So in an n-dimensional space, there would be n-1 dimensional. Let's just try to see this in examples. Yeah, so this is a typo. So this is 1/2. So here I have two column vectors. This one and this one. And it sticks out here, or it sticks out here. And there is an associated hyperplane, which is orthogonal to it. So it's a normal vector of some hyperplane, but it's actually a one-dimensional thing. If you consider the same thing as a row vector, then these are again the slices for different values, the one form. It is a hyperplane for each, it really is a hyperplane for each value that you will see. So for each fixed value, in particular here in the middle, it's just this one. So this is the value equals 0. And here you might not be able to see it, but it's actually not too bad. It's 0, right? And it's just a collection of them. In particular, while the vector itself is just one-dimensional, the one form is kind of two-dimensional. Each slice is a two-dimensional space. It's a whole plane of vectors, so all of these all vectors that kind of lie in this blue plane will pair with V. Let's call them W. Will pair with W with V to 0. Yeah, and that's what there is to say. Well, there's a lot of there are a lot more things I could say about duality, or at least someone could say about duality. Um, but the general philosophy is really there should be some two sides of the same coin, and for vector spaces, it's like transposing matrices or vectors. Because if you think about it carefully, who decided that vectors need to be column vectors, not row vectors? There's a decision somewhere, and the flipping is exactly going to the dual vector space. Okay, that's it. Thank you very much. Hope to see you next time.